Okay, so what we're going to have a bit of a look at now is our confidence intervals. All right. So the sample proportion itself can be used to estimate the population proportion. Okay, that's fair enough. And it's called an estimate. I guess what we want to look at then is, okay, if we're going to use a value to estimate P, well, how reliable is that? Okay, so what we tend to try and do is come up with an interval that we can be reasonably confident the P value will fit into. Okay, so that's my confidence interval. Now we know previously that with our normal distribution, basically within 2 standard deviations of the mean is 95% of our data, isn't it? 2 standard deviations. All right. Now what we can actually show on our calculator that it's not quite 2 standard deviations. In fact, it's exactly 1.96 standard deviations. All right. So what we're saying is to come up with a confidence interval, instead of doing 2 times, instead of doing the mean minus 2 standard deviations, the mean plus 2 standard deviations, we're going to do the mean minus 1.96 standard deviations and the mean plus 1.96 standard deviations. So the 1.96 really is just a more accurate number of standard deviations from the mean, or from p hat in this case. All right, so let's have a look. So find an approximate 95% confidence interval. Let's get a bit of size here. For the proportion of primary school children in Australia who regularly use social media. Okay, if we select a random sample of 20, find the sample proportion. And find the sample proportion to P 0.7. So we're saying that P hat was 0.7, the proportion of kids in our sample. So what do we need? We need a mean and a standard deviation, don't we? So we know the mean is simply P hat, which is equal to 0.7. And my standard deviation, well, we won't even worry about this going to standard deviation. Let's just go straight to our rule, won't we? So my 95% confidence interval is P minus 1.96 times the standard deviation, which is P times 1 minus P over N, to the mean plus 1.96 standard deviations, P 1 minus P over N. So for us, it's going to be, well, my mean was 0.7 minus 1.96 times the square root of 0.7 by 0.3 over sample size of 20, 0.7 plus 1.96 times the square root of 0.7 by 0.3 over 20. So if I work that out on my calculator, I'm going to get 0.499 to 0.901. So what we're saying here is that we think that 95% of our sample proportions will fit within that interval. Okay, so in some ways, so 95% of sample p hats fit in this interval. Okay, so obviously when we take a sample size of 20, it's not going to be such a reliable estimate. So what happens if instead, if we increase our sample size to 200, what sort of an interval will we come up with then? So using exactly the same calculations, 0.7 minus 1.96 times the square root of 0.7 by 0.3, this time over 200, and 0.7 plus 1.96 times the square root of 0.7 by 0.3 over 200 will give me 0.636 to 0.7, Shit, I can't remember. 3, 4. Correction. 0.764. So already, so now we're saying 95% of our p hat. So if we get, if each of us do 20 samples, if we do our own 20 different random samples, we would expect 95% of those sample values to fit within 0.63 and 0.76. Okay. So in other words, we think 0.636 times 200, which is what, say 126, to 0.76 times 200. Yeah, so about 126, and 0.764 by 200, say 152. So we might expect between 126 to 152 of our students, of the 200 students, to be using social media. Okay, so if we follow that through, obviously if that 0.7 there is what we've observed, okay, well then this part of it here can be considered the error. Yeah, so we're saying it should be 0.7. Well, whatever we subtracted from 0.7 and whatever we added to 0.7, which in this case is 0.64, well, that's the margin of error that we've got. Okay, and so that section of the formula, okay, is considered our margin of error. So it's the distance from the endpoints of the confidence intervals to the sample estimate. All right, so let's keep working through. Determine the sample size required to achieve a margin of error of 2% in an approximate 95% confidence interval. So what we're saying there, so we want, let's go through it. So we want the margin of error to be 2%. I've got a 95% confidence interval, which means it's 1.96 standard deviations, and we know our proportion is 0.7. So that means my margin of error, which is, if you like, 2 out of 100, has to equal 1.96 times the square root of 0.7 by 0.3 over whatever n happens to be. Yeah? So if we transpose, so 0.02 over 1.96, I'm then going to square that. That'll equal 0.21 over n. So let's work that out. Yep, and if we bring all that together, that's going to give me n approximately equal to 2016.84 people. So I'm going to need a sample size of 2017 people to ensure an error of less than 10%. Okay? 10, or did I say 10? 2%. So a 95% confidence interval for a population will have a margin of error approximately equal to a specified value of m, and the sample size is. So this is really just, there's certainly not formulas given on a formula sheet, but maybe they're worth marking down. It's just the formula above rearranged. So that will help you work out a specific sample size. Okay. It was 0.636 to 0.764. Let's keep working through. Now, the only thing you've got to be aware of is that it is possible that we may need to change the confidence interval. All right. So we spoke about how in the formula that we've been using, this K value here has been up to now just 1.96. And the reason it's 1.96, because if I do the inverse norm, 0.95 of a 0, 1 distribution, that's approximately equal to 1.96. Okay, so to get a 95%, I tell a lie, hang on, it's not 95, it should be, in fact, if I want a 95% confidence interval, I want a 95% confidence interval, I want those two things to be 2.5%, don't I? So in actual fact, if I do 0.975 on a 0, 1, I get approximately 1.96. Using the same logic, if I wanted to say get a 90% interval, it means that I want 90% between there and there, which means that's 5% there, yeah, 5% there. So I'm almost saying this here, aren't I? I'm saying the probability that whatever the K value happens to be is going to be equal to, in this case, 95% or 0.9, or 90%, we'll say, 0.9. And if I use, so if I go to inverse norm, to be less to that point there, it's going to be 0.95 on a 0, 1. I get 1.644, so 1.64. Okay, so and if I want to do the same thing, so if I want to work out a K value, then for 90% confidence interval, my K value is equal to 1.64. For a 95% confidence interval, the K value is equal to what we'd already had, 1.96. And a 99% confidence interval, K is going to be equal to 2.58. So it kind of makes sense that the more accuracy that we want, the K value's got to get bigger, because if it gets bigger, it means that this, what I'm adding and subtracting from my P hat value gets bigger, which means I'm going to get a broader interval, which means I can say with more confidence that my value will be within that interval. All right. So if I just write down the rules for you, so for a 90% confidence interval, let's have a look. For a 90% confidence interval, I'm going to have 0.7 minus 1.65 times the square root, 0.7 by 0.3 over 200, 0.7 plus 1.65 times square root, 0.7 by 0.3 over 200, and that will give me 0.647 to 0.753. My 95% confidence interval I've already done. I can't remember what was that interval? It was from memory, just dragging the chain. What was it from memory? I've got no idea. So it was 0.636 to 0.764. And now if I want my 99% confidence interval, I'm going to have 0.7 minus 2.58 times 0.7 by 0.3 over 200, 0.7 plus 2.58, 0.7 by 0.3 over 200. which will give me an interval size, of 0.616 to 0.784. Okay, so notice as the more confidence that we want, the bigger the intervals become. And that kind of makes sense. If I'm saying my value is going to be between these 2 points, well then if I pick really wide points, I can be really confident it'll be within there. All right, give it a go.